This is a Chem Study film, a production of the Chemical Education Material Study. Here are 4 different liquids. We shall study their properties in developing a model which relates chemical properties to molecular shape. Let's look at some electrical properties first. Here is a sphere which has been given a positive charge. After rubbing this hard rubber rod with cat's fur, the sphere and the rod attract each other. Since the sphere is positively charged, this is good evidence that the rod has acquired a negative charge. Now notice how the negatively charged rod attracts a stream of water from the first bottle. Here is a stream of acetone. It too is attracted. Let's try the other liquids, carbon disulfide and benzene. The charged rod does not attract carbon disulfide. Nor does it attract benzene. Why does a negatively charged rod have no effect on carbon disulfide and benzene, and yet does deflect water and acetone? Is it possible that the streams which are deflected are charged positively and the others are electrically neutral? If this is true, a positively charged rod should repel the deflected streams. A glass rod rubbed with silk repels our sphere. The glass rod is electrically positive, as shown by its repulsion of the positively charged sphere. Let's try this positive rod on water. That's strange. The stream is attracted, just as it was by a negative charge. Let's try the other liquids. The acetone is also attracted, just as it was by the negative rod. Here is carbon disulfide. No effect from the positive charges. This is the same result as with a negative charge. This is benzene. No deflection. Again, the same result as with a negative charge. So we see that some liquids are not deflected by either kind of charge, while other liquids are attracted by both positive and negative charges. Why? Here is a tabulation of our findings. Water and acetone are deflected. Carbon disulfide and benzene are not deflected. How can we account for these different electrical properties? How can water, for example, act in one case as if it has a positive charge, and in another case as if it has a negative charge? To answer this question, let's see if we can construct a model or concept on the molecular level that accounts for the deflection or lack of deflection in these experiments. As a first step, let's consider the structure of water on the molecular level. The hydrogen atoms share electrons with the oxygen atom. As you have learned, the shared electrons are more strongly attracted by oxygen than by hydrogen. The increase in electron density near the oxygen makes this region of the molecule slightly negative. The lack of electrons around the hydrogen gives this region a small positive charge. Such a separation of positive and negative charge is said to form a dipole. An arrow is often used to represent a dipole, with the head of the arrow pointing toward the negative charge. Since there are 2 such bond dipoles in water, the combination gives a resultant molecular dipole, even though the molecule as a whole is electrically neutral. The dipole for any molecule can be represented in this manner. One end negative and the other positive. If a positively charged rod is brought near a dipole, like charges repel, unlike charges attract. This orientation results. On the other hand, if a negatively charged rod is brought near a dipole, the opposite orientation results. Thus, dipoles will be attracted toward either positive or negative rods. So we can understand why a molecule with a shape like water can be attracted by a positively charged rod. Our model also explains the attraction by a negatively charged rod. But let's see if our model applies to the behavior of our other deflected substance, acetone. Acetone consists of a central carbon atom with an oxygen atom on one side and two CH3 groups on the other. Because the oxygen atom has greater attraction for electrons than does carbon, consistent with the ionization energies, one end of the molecule is negative. The other end is positive. Therefore, acetone has a dipole. Any molecule that has a dipole is called a polar molecule. Thus far, we have accounted for the behavior of water and acetone. Now let's see if we can account for the behavior of the non-deflected substances. We'll begin with carbon disulfide. The molecule consists of two sulfur atoms and one carbon atom. There may be a dipole between the carbon atom and each sulfur atom, but because the molecule has a linear shape, with the two ends identical, the two dipoles cancel each other. Such a molecule is called nonpolar. We recall that a polar molecule has a separation of charges which causes the molecule to align itself toward a charged rod. In a nonpolar molecule, there is no separation of charge, so there is no strong interaction with a charged rod. Let's consider the charge distribution in the other non-deflected molecule, benzene, C6H6. Because of the highly symmetrical shape, any bond dipoles in this molecule also cancel each other. Thus, benzene, too, is nonpolar. So we see that bond polarities and molecular shapes determine whether molecules are polar or nonpolar. To test our model of molecular dipoles, let's see if we can predict the effect of shape on the polarity of molecules. Here are two forms of dichloroethylene. One is called cis-dichloroethylene. The other is called trans-dichloroethylene. They have the same formula, but their structures are different. How will their differences in structure affect their behavior? In the cis, the two chlorine atoms are on the same side of the bond joining the carbon atoms. Chlorine atoms attract electrons more readily than do hydrogen atoms. Therefore, the cis molecule should be polar. In the trans-dichloroethylene, the chlorine atoms are on opposite sides of the bond, so the positions of the chlorine atoms create opposing dipoles which cancel one another. Therefore, the trans molecule should be nonpolar. The polar cis molecule should be deflected by a charged rod, while the nonpolar trans should not be deflected. Let's try the nonpolar trans first. It is undeflected. Now the polar cis. It is deflected. Our predictions were correct. Thus far, our deflection experiments have allowed us to develop our model, but such experiments cannot supply us with quantitative information. Here is an apparatus which gives more precise measurements of the effects of charges on dipoles. The liquids to be tested are placed in this cell. The sides of the cell are metal plates which can be charged electrically. The plates are attached to an apparatus which can force a charge to oscillate from plate to plate. In other words, just as a pendulum swings, there can be a motion of electrons back and forth from one metal plate to the other. A meter called an oscilloscope is used to detect the rapid movement of charge from one plate to another. On the scope, time is indicated in the horizontal direction and charge in the vertical direction. A spot on the scope moves up until the maximum charge is reached. Then a little later, the spot moves down until maximum charge in the reverse direction is reached. Let's watch the apparatus in operation. As the oscilloscope warms up, the charging pattern appears. Nonpolar trans-dichloroethylene is in the cell. We see the tracing spot as a continuous curve on the scope, since the flow of electrons reverses direction many times per second. The distance between vertical lines of the scale corresponds to 5 microseconds. Thus the charging time is 17 microseconds. Now the cell has been filled with cis-dichloroethylene. The charging time with this polar substance between the plates is 29 microseconds. Why has the charging time increased? Let's return to our model. With a polar molecule between the plates, the electric forces cause the dipole to align in this manner. Then the charged ends of the dipole will attract additional electric charge onto the plates. Thus a polar substance should require more charging time. With nonpolar dichloroethylene, the time was 17 microseconds. But with polar dichloroethylene, it was longer, 29 microseconds. Now suppose we further test our model by investigating the effects of temperature. Up till now, we have portrayed the molecule at rest. But we know there are actually many molecules present, all in random jostling motion. Their jostling motions disrupt the dipole orientation. But at a lower temperature, the jostling motion of the molecules is reduced, though they still occasionally tumble. The greater average alignment at the lower temperature should attract more charges onto the capacitor plates. Therefore, we predict that the charging time for a polar substance should increase at lower temperatures. We'll chill the polar substance, cis-dichloroethylene, to 0 degrees centigrade. Insulating lacquer on the outside of the cell prevents electrical conductance through the water in the ice bath. As the cis cools, the charging time does increase. Here are the previous charging times. After thorough cooling, the cis time becomes 37 microseconds, somewhat longer than at room temperature. Since trans-dichloroethylene is a nonpolar substance, there is no alignment between the plates. Therefore, varying the temperature should have little effect on the charging time. After chilling, the charging time is still 17 microseconds. So we see that at 0 degrees, the charging time for trans is the same as at room temperature. These effects of temperature upon charging time give further evidence that our model is correct. Now let's see how our dipole model can explain other differences in physical and chemical behavior. For example, differences between water and benzene. HCl gas, a polar substance, has been placed in the stoppered tubes. Now watch what happens inside the tube as we remove the stopper. Well, that was rapid. HCl gas certainly dissolves readily in water. Now let's try HCl and benzene. Quite a contrast. Careful observation is needed to see that the benzene level actually is rising. Here is the level about 5 minutes later. And here about 15 minutes later. Let's drain out the two solutions and compare some of their properties. We'll measure the conductivity of the two solutions, first placing silver electrodes in each beaker. Touching the probes causes a meter deflection, which indicates conductivity. However, the HCl in solution in benzene does not conduct appreciably. By comparison, HCl in water is a conductor. How do we account for this difference? Let's consider the molecules of the two solutions. With polar hydrogen chloride in nonpolar benzene, collisions occur, but the nonpolar nature of benzene does not encourage ion formation. However, when a polar hydrogen chloride molecule and a polar water molecule collide, reaction can occur. The surrounding water dipoles hydrate both ions, forming aqueous hydrogen ion and aqueous chloride ion. The resulting ionic solution is a good conductor. Note the orientation of the dipole arrows. The orientation around the positive hydrogen ion is opposite from that around the negative chloride ion. Since HCl is present in water as ions and in benzene as neutral molecules, we might expect the chemical behavior of the two solutions to be different. Let's test their reactions to magnesium metal. First, the solution of unionized HCl in nonpolar benzene. It produces no visible reaction. Now the ionic solution of HCl in polar water. Well, that's different, all right. A gas forms, a gas which is found to be hydrogen. The hydrated ions in the polar water react rapidly. The unionized molecules in the nonpolar benzene do not. Ions hydrate in polar water for the same reason that water is attracted by a charged rod, regardless of whether it is negative or positive. Polar molecules can align either way. Likewise, the concept of polarity correctly predicts and interprets the effect of temperature on dipole alignment. Our dipole model also correlates differences in solvent properties. It interprets the conductivities of the resulting solutions. And it accounts for their different chemical reactivities. A knowledge of the shapes and polarities of molecules is a powerful tool for interpreting the chemical properties of substances.